In the late 19th century, scientists studying the relationship between light and electricity began hitting a wall. Their experiments were producing results that the classical physics of the day could not explain. Physicist Wilhelm Hallwachs set up a specific experiment to investigate. He attached a piece of zinc to a gold leaf electroscope. An electroscope is an early scientific instrument used to detect the presence and magnitude of an electric charge. He charged the zinc negatively. Inside the jar, the gold leaves repelled each other and stood apart, indicating the presence of that charge. But the moment he directed a beam of ultraviolet light onto the metal surface, the leaves collapsed. The negative charge disappeared. The results grew more complex. If he directed that invisible light onto an uncharged piece of zinc, the metal acquired a positive charge. And if the zinc was already positively charged, exposing it to the ultraviolet beam made that positive charge even stronger. The physical evidence suggested a single conclusion. The ultraviolet light was physically stripping negatively charged particles right out of the solid metal. This behavior directly challenged the established theories of light as a continuous, smooth wave. To figure out exactly what was leaving the metal, physicist Philip Lenard took the investigation a step further. He tracked these escaping particles by isolating the metals inside a complete vacuum. He built a sealed glass tube containing two separate metal electrodes. One is emitter plate C, and facing it across an empty gap is collector plate A. He wired both plates to a battery, creating a deliberate electric field between them. Because standard glass blocks ultraviolet rays, Lenard integrated a special quartz window into the side of the tube. Quartz is transparent to ultraviolet light, allowing the beam to pass straight into the vacuum and strike the emitter plate. When the ultraviolet rays hit the surface, they transfer enough energy to the surface electrons to break them free from the attractive pull of the metal's ions. The electrons eject directly into the empty space of the tube. Once they are free, the electric field generated by the battery takes over. It pulls these negatively charged electrons across the gap and into the positive collector plate. This physical movement bridges the gap and completes the electrical circuit. The connection is instantaneous. The second the ultraviolet light is blocked from entering the window, the flow of electrons stops. Scientists named this resulting stream of electrons the photocurrent. Photocurrent is a measurable electrical flow from matter caused by the interaction with light. They finally had concrete proof that light could strike solid matter and generate a steady current. Having trapped the phenomenon in a vacuum tube, researchers could measure exactly how much electricity the light was producing. They placed highly sensitive microammeters into the external wiring, instruments designed to measure extremely small electrical currents, down to 1/1,000,000th of an ampere. When they moved the light source closer to the emitter plate, increasing the intensity of the beam, the needle on the dial moved higher. Doubling the light's intensity exactly doubled the number of emitted photoelectrons detected in the circuit. But there was a catch. If they changed the color of the light to a lower frequency, like red, the needle stayed at 0. They could turn on the brightest, most intense red spotlight imaginable, and no electrons would leave the metal. The data revealed a precise set of rules. The interaction between light and the electrons inside the metal was dictated by frequency, not just brightness. The rules governing this interaction depend entirely on the frequency, the actual color, of the incoming light beam. Think of the electrons in the zinc plate as being trapped at the bottom of a well. Low-frequency light waves do not carry enough energy in a single hit to knock an electron out of that well, regardless of how intense the beam is. Meanwhile, a high-frequency ultraviolet beam delivers sharp, highly energetic impacts. Even if the ultraviolet light is extremely dim, the individual hits it does deliver are strong enough to launch electrons out of the metal instantly. This graph shows a frequency spectrum with a hard cutoff line. Physicists call this the threshold frequency. It is the absolute minimum frequency of light required to liberate an electron from a specific material. Any frequency falling below this line fails to trigger emission. This cutoff demonstrated that light doesn't deliver energy as a smooth wave. Instead, it interacts with matter in discrete, concentrated packets. Each individual packet must meet a strict minimum energy requirement to move an electron. That specific threshold value is not universal. It changes based on the properties of the metal used as the emitter. Zinc binds its electrons tightly, requiring the high-frequency impact of ultraviolet light to knock them loose. But alkali metals, like lithium and sodium, hold their outer electrons more loosely. Because of this, even standard, visible room light carries enough energy to trigger electron emission in them. Materials that readily emit electrons when illuminated are known as photosensitive substances. Identifying these materials made it possible to design modern light-sensing technology, from automatic doors to digital cameras. Hallwachs and Lenard provided the quantitative proof that light delivers energy in concentrated units. Their work shifted the scientific view of light from a continuous wave to a stream of particles, providing the measured values that allowed physicists to describe the behavior of individual electrons.